All right, people. All right, people. So, what's up, people? I believe everybody is doing great, nice, and absolutely fine. Welcome to Unacademy NEET English. Okay, I believe all of you are doing great, nice, and absolutely fine. And guys. So this session is super important for all the students out there who are going to write exam. I would say on 5th of May. Okay. So we will be discussing 10 guaranteed topics which have the maximum probability that they can be asked in your NEET exam. So we will be discussing those as well as even they are more than 10, as well as I will be showing you the problems on those and from the scratch also. Okay, if you haven't studied these topics before, I'll 100% there is guarantee that you will be able to understand each and every single point. Okay, so this session is super important for you guys. You should not miss out any of these topics if you're writing the exam tomorrow, if you want to enter the medical college, okay, in the upcoming time. So, and most importantly, if you have not liked this session yet, I want you guys to hit the like button as soon as possible, because liking this session is mandatory. Everybody out there, call up your friends, tell everybody that this session which I'm going to take right now is super important. Tell your friends so that they can come and join this particular session. Okay, okay. So everybody in the chats, show some fire, show some love in the chats. Everybody, guys, I just want to see in the chats. Okay, light up the chat box as soon as possible. Okay, guys. So this is, we say, super important. Let the people join and we are starting the session accordingly. I am waiting for everybody to join and we will start this particular session. And let me just tell you one thing. In the evening at 7 p.m. we have got the NEET replica. Okay, that paper which has, we say, the maximum probability that will come in the NEET tomorrow. So I want you guys to join that session also in the evening, everybody of you. Okay, I hope you have liked this particular session. Okay, guys, there are so many people watching and likes are less. So make this like count. I want everybody of you to make it 1000 as soon as possible. Everyone means everyone. Okay. So I think we need to start the session now. Everybody listen to me very carefully. Let's start with the first concept that we have over here on the screen. That is we say, let's basically go with this concept. That is the concept from, we say, escape velocity. Everybody, this is a very important concept when it comes to basically your NEET. This is from the gravitation. What is this escape velocity? Guys, listen to me very carefully. Call up your friends. Tell everyone there is a super important session going on Unacademy NEET English channel. So join it as soon as possible. Now see, guys, everybody of you, listen to me very carefully. When it comes to the escape velocity, we say it is the minimum velocity with which a body escapes from the gravitational field of Earth. Okay, what I'm trying to say is that let's suppose I say I have got, this is the Earth over here, and you are throwing this object something like this. We say it goes up, and then it falls back onto the Earth. Now let's suppose if you are giving more velocity to it, it goes and it again falls back to the Earth. Now if I say you give it a decent amount of velocity, if you give that velocity, we say it goes and it does not come back. So means it escapes from the gravitational field of Earth. That velocity is what we call, we say, escape velocity. That velocity is what we call escape velocity. Okay. Now here, my dear friends, we have got Earth over here. The mass of Earth is m, the radius is r. And there is an object which is placed over here. I am saying that you have to give this object some velocity. You have to fire this object with some velocity so that it escapes the gravitational field of Earth. Okay. And What is that velocity? That velocity is what we call, we say, sir, escape velocity. That velocity is what we call escape velocity. Okay. And what is the value of that velocity? Guys, the value of that velocity is simply, we say, v is equal to under root of 2 gm by r, where g is the universal gravitational constant, m is the mass of earth, and we say r is over here the radius. Okay. And my dear friends, if you put the values over here, we say it will come out to be 11.2 kilometer per second. So means if you give this much of velocity to an object, it will escape from the gravitational field. Now, this is the escape velocity in terms of mass. If we have to find the escape velocity in terms of density, we say this is the formula. This is the formula, r under root of 8 by 3 g rho and pi. This is the formula for the escape velocity in terms of we say density rho. Okay, density rho. Now guys, listen to me very carefully. Listen to me very carefully. Let's move on to this particular question that we have exactly over here. All the people out there, listen to me very carefully. I hope you have liked the session. Everybody of you like the session as soon as possible. We say, the question says that the ratio of escape velocity at Earth is VE to the escape velocity at planet is VP, whose mean radius. Okay. Let me show you what does the question say. It says that we have, let's suppose, got Earth over here. Okay. So we have this Earth over here. Now, if I say, my dear friends, we have got over here, this is a planet over here. Okay. The questioner says that there is an object, this is Earth, and this is planet. The questioner says that you have to launch this object with escape velocity VE. And if you are launching the object over here, you are launching this object with a escape velocity that is over here, escape velocity at this planet. Okay. At this planet, we say escape velocity is VP. On this Earth, escape velocity is VE. Now, guys, if I say in this particular case, listen to me very carefully. We say density of Earth, we say radius of Earth is, let's suppose, RE, density of Earth is, we say, rho E. And we say radius of this planet is given as 2 times a radius of Earth. You can see over here, whose radius and mean density are twice as that of Earth. So density of this planet is also given as 2 times of R, 2 times of rho P. Okay. Now, guys, what we are supposed to find in this particular case is what is the escape velocity at Earth divided by escape velocity at that planet. Escape velocity at Earth divided by escape velocity at that planet. Now, clearly you can see over here, the radius is given, density is given. Radius is given, density is given. Don't you think that we should use this formula? Because in this formula, radius is there, we say density is there. If we use this formula, we'll get the answer. So can I say in this particular case, everybody out there, can I say in this particular case, we say escape velocity. What is the formula for escape velocity? That is R under root of, we say, rho 4 by 3 pi. We say A under root of 8 by 3 g rho pi. We say 8 by 3 g rho pi. Now, guys, tell me one thing. We say, sir, in this case, 8 by 3 is constant, g is constant, pi is constant. Can I say this escape velocity is proportional to, we say, r and under root of rho? So these are the two things at which escape velocity is depending upon over here. Now, can I say escape velocity at Earth will be simply, that is radius of Earth under root of density of Earth upon escape velocity at planet. We say that will be radius of planet. How much is the radius of planet? That is 2 times the radius of Earth. Under root of density of planet. How much is the density of planet? We say that is 2 times density of Earth. That is 2 times density of Earth. Now, this RE, this and this will get cancelled. So it will be 1 by 2 root 2. So this is the ratio of escape velocity at Earth and we say at that planet. Okay. This was the first concept, escape velocity concept, which was important. Next concept over here is one more. This is from the Now see, if let's suppose this is the concept number 2. If let's suppose we have got the capacitors over here, these are n capacitors. This is very important. So many times the question have been asked from this in your NEET. If we say we have got n capacitors, small capacitors over here, and we combine these n small capacitors to form a big capacitor. Okay. Now I ask you, how much is the capacitance of big capacitor? How much is the potential of big capacitor? How much is the radius of big capacitor? And how much is the charge stored on the big capacitor? Guys, I say charge on the small is small q. Okay. Potential of this is, we say V. Radius is small r. Now listen to me very carefully. So we say charge on this big capacitor, directly you say, if these are n capacitors, we say Q is equal to n times of Q. If this is 27 capacitors, we say Q is equal to 27 times of Q. And radius will be n raised power 1 by 3 into r. Guys, you have to directly remember it. You'll be solving the question in the exam by using, if you use these formulas in just seconds. Okay. And capacitance of the big capacitor will be simply n raised power 1 by 3 into C. N raised power 1 by 3 into C. And we say potential of this big capacitor is, we say V dash is equal to n raised power 2 by 3 into V, where V is the potential of the smaller capacitor. Now guys, listen to me very carefully. There is a question which was asked on the same concept, in NEET 2021. It says that we have got 27 small drops. Either you say drops or you say capacitors. We say these are the 27 capacitors, means n is equal to 27 over here. And they are combined to form a, we say, big capacitor. Okay. And we say potential of these capacitors is given as 220 volts. Potential of each capacitor is given as 220 volts. You guys are supposed to find the potential of the big drop. Which formula I should use over here? V dash is equal to n raised power 2 by 3 into V. So I say V dash is equal to n raised power 2 by 3 into V. Now what is the formula for V dash over here? We say V dash is equal, what is the value of n? That is 220. Value of n is 27. N is 27 over here. Whole raised power 2 by 3 into V. So can I write it just something like this? So we can write it, this is 27 and then it is 1 by 3 into 2 into V. So that is also 2 by 3. So we can say this will be something like this. Cube root of 27 is 3, because 3 into 3 into 3 is 27. We say, sir, this will be 3 and this is square into V. So 3 square is 9, 9 into we say V. Now what is the V is the potential of smaller drop, that is 220. So we say 9 into 220, answer will be 1980 volts. So potential of the big drop is 1980 volts. Even if somebody asks you find the capacitance of the big drop, you can find that by using this formula. You can find the radius of big drop, you can find the charge of the big drop. This was also the super important concept that I wanted to discuss over here. Next concept is conservation of mechanical energy. What does conservation of mechanical energy say? It simply says that we say total energy initially is equal to total energy finally. Okay, like over here, total energy initially is equal to total energy finally means kinetic energy initially plus potential energy initially is equal to kinetic energy finally plus potential energy finally. Everybody of you know this conservation of energy. Now on this conservation of energy, there is a concept which is over here. You have got this mass, you have got this mass over here. Okay. Now guys, we say there is one more mass which is placed over here, that is this m. What should be the velocity given to this mass? What should be the velocity given to this mass so that it escapes from the gravitational field of two spheres? Guys, here we'll use the conservation of energy. What does that say? That says total energy initially is equal to total energy we say finally. Guys, initially we say this is over here, this mass is over here. Finally, this mass will be at infinity, because when it escapes from the gravitational field, we say it will go to the infinity. We say it will go to the infinity. Okay, it will go to the infinity. Now, when this mass is exactly over here, can we write the total energy over here? Total energy in this case will be potential energy plus kinetic energy. I can say when the mass is over here, we say potential energy will be how much? Between this mass and this much, how much will be the potential energy? Minus G capital M small m divided by, we say distance is 3r, that is 3r. Okay. This is the potential energy between these two. Now, potential energy between this and this will be minus Gm1, M2. M1 over here is 2m, 2m. M2 is this mass, that is m, divided by distances, we say, sir, 3r over here. Okay. And then we say plus. Guys, I have to write total energy initially. How do I write total energy? Kinetic energy plus potential energy. So this is the potential energy net initially. Kinetic energy initially is how much? We say, sir, 1 by 2 mv square. If we are talking about this mass, we say first we'll check the potential energy between this and this, between this and this. Then how much is the kinetic energy of this mass? That is 1 by 2 mve square. So this VE we are supposed to calculate if we basically place it over here. How much velocity should we give to it? Now guys, listen to me very carefully. I can say is equal. This is total energy initially. Finally, this mass is at infinity. So we say at infinity, potential energy we consider as 0 plus kinetic over energy also over there. We say, sir, it will be, we say 0. It has finally escaped from the gravitational field. Now, follow this particular thing. See, this is 2gmm by r square and plus this is minus and this is also minus. So this will be 3 times of. I'll write over here. So this will be basically minus 3 times of G capital M small m divided by 3R is equal to, okay, is equal to, I say over here. So this will be plus 1 by 2 mve square is equal to 0. Now I want you guys to take it over there. So this will be 1 by 2 mve square is equal to 3. 3 and 3 will cancel. So this will be over here. That is G capital M small m divided by R. Okay. Now this and this will also cancel. So VE square will be 2G capital M divided by, we say, R. VE will come out to be under root of 2gm by r. Basically, I could have told you directly this. But why I wanted to tell you this, why I wanted to basically show this particular question, so that you'll get to understand the feel of conservation of energy. How do we apply this in? We say in the questions. Okay. Next, we have the energy of the satellite, which is very important. Okay. Now, guys, when it comes to the energy of satellite, listen to me very carefully. You have got Earth over here. Okay. We say at this distance, we say this is the radius of Earth is capital R. At height h, you are launching an object, okay, which revolves around this planet, which revolves around this Earth. And this is what we call the satellite. Now, guys, listen to me very carefully. Mass of satellite is m. Velocity of satellite is v. So and it is performing the circular motion over here. Whenever the satellite performs the circular motion over here, whenever it is in the motion, so we say any body is in motion, it has kinetic energy. So this satellite will have the kinetic energy, that is G capital M small m divided by 2r. G capital M small m by 2r. Capital M is the mass of Earth, small m is the mass over here, divided by 2r in this particular case. R is this R is capital R plus h. And guys, if you have got two masses over here, you have one mass and you have another mass. So means there is potential energy. Whenever you have two mass separated by some distance, there is potential energy. How much is that? That is U is equal to minus G capital M small m divided by R. Next, guys, we say there is also kinetic is there, potential is there, so means there is total energy. So we say kinetic is equal to total energy is kinetic plus potential energy. So kinetic energy will be G capital M small m divided by 2R. Potential energy will be minus G capital M small m divided by R. So if you subtract it, it will be simply that is minus G capital M small m divided by 2R. This will be the value of total energy. Now guys, listen to me very carefully. If somebody asks you to plot the graph between E versus R, over here you can clearly say that kinetic energy is inversely proportional to R. See, we say kinetic energy is inversely proportional to R, and this is positive. Value of this is positive. Potential energy, we said this potential energy is inversely proportional to R, but it is negative. And when it comes to the total energy, it is also inversely proportional to R, and it is also negative. So that's the reason we have made the graph of kinetic energy from upper side. Why we say kinetic energy is positive. And graph will be rectangular hyperbola only. And these two are, we say, negative. That's the reason we have made the graph from lower side. This is very important. Same graph we make when electron revolves. If we say this is the nucleus over here, and around the nucleus, if I say electron is revolving with some velocity, its mass is m. In this case also, it will have kinetic energy, potential energy, and it will have total energy. Graph will be exactly similar for this case also. This I have told you in the modern physics. Okay. Now there is one more concept. There is one more concept which is important. Okay, which is important. That is potential due to a hollow or solid, hollow sphere and solid sphere. Guys, remember one thing. This is an important concept. If I say I have got a sphere over here, and charge on the sphere in this case is, we say, sir, plus q. Okay. Now, my dear friends, we say at small r distance, because of this, potential will be kq divided by r. Okay. And we say, if we say on the surface, we say potential will be kq divided by r. This is potential because of, we say, hollow sphere. Next, and inside also it will be kq divided by r, And when you make the graph between potential versus r, so it will be something like this. Inside it is constant, outside it will be rectangular hyperbola. Why is it constant inside? We can say, sir, inside it is kq by r. K is constant, Q is constant, radius of this sphere is also constant. So we say this is constant. So that's the reason the graph is something like this. Okay. Now, what is important more over here? If you have got a solid sphere, means solid sphere is that sphere in which charge is present inside. So I say, because of this solid sphere, potential outside will be kq by small r. And potential on the surface will be kq by capital R. And potential inside will be kq by 2r cube, 3r square minus small r square, where small r is the distance inside. And potential at center is this. Here, this graph is very important. That's the reason I have put up this question over here. Now, guys, listen to me very carefully. We say graph in case of solid sphere will be something like this. At center, potential will be highest, that's 3 by 2 kq by r. Okay. And then this is the potential on the surface, that is kq by r, and outside it is inversely proportional to small r. Okay. Next. Okay. There is a concept from, we say, ray optics. That's what we call the concept of apparent depth. Very famous concept. You all might have heard about this particular concept. Now see, what does this concept actually say? I want you guys to focus over here. Guys, see, let's suppose we have got a bucket over here. Inside this bucket, there is a water, okay? Or you have got a swimming pool, there is a water inside that. And you have placed an object inside this one. You are the observer which is looking from the top. Have you ever experienced this? If object is placed at this distance, okay, distance D, depth D, it feels like it is placed somewhere around over here, okay? It is not at that distance, it is at a much lesser distance, much lesser depth. You might have observed this. It feels like if you have placed, we say, a stone in the water, it feels like it is not at at large depth. It is at very small depth, so we can see it very clearly. So the depth at which observer or our eyes basically see this object, that is what we call apparent depth. Actual depth of this object is this, but this is apparent depth. And what is the formula for apparent depth? That is d dash is equal d upon mu I by mu r. D is the actual depth, and mu I is what? Mu I is the refractive index of that medium in which incident rays are present. Now see, if I say this is the object, everybody knows that we say incident rays leave from the object. Incident rays leave from the object. Okay, so in this case, mu I, we have to take this, and mu r will be that. We say that medium in which refracted rays are present. That will be this one. Now, guys, tell me one thing. There is a question which is mentioned over here. I want you guys to exactly focus on this particular question. Okay, now see what this question actually says. We have got a tank over here, and inside this tank there is, we say, water filled, and there is a fish which is placed inside this water, and there is a bird at the top. Bird is at 36 centimeter height from the water, surface of water, and we say this fish is at 24 centimeter in depth from the surface of water. Fish is at the depth of 24 centimeter. This is at 36 centimeter height. Find the apparent depth of fish with respect to the bird. We have to find, see, this is the actual depth of fish. At what depth this bird would be able to see this fish? We say if we have to find the apparent depth, that is a d upon mu I divided by mu r. This is the simple concept. What d means actual depth. What is the actual depth of this fish? That is 24. I'll write 24 upon. Now, mu I by mu r. Mu I is the refractive index of that medium in which object is present or in which incident rays are present. This is the object over here, and bird is observer. We are finding the depth of fish. So we say refractive index of this is given as, that is 4 by 3 upon. Now, mu r is the refractive index of that medium in which refracted rays are present. That will be the upper medium, that is air. So for air, refractive index is 1. So this will be simply, that is 24 into, we say, 3 by 4. 4 ones are 4 6s are. And 6 into 3 is, we say, sir, 18 centimeter. So means actual depth of this fish is 24, but this bird will see this fish at what depth? 18 centimeter depth. Then it asks, find the apparent height of bird with respect to the fish. Now see, we have to find apparent height of bird with respect to fish. Now guys, tell me one thing. Now fish is the observer and bird is the object. Okay, if we have to find at apparent height, see, actual height is 36. What is the apparent height? H dash is equal to h upon mu I divided by mu r. Same formula. H means actual height. Actual height is, we say, sir, 36 divided by mu I. Mu I is the refractive index of that medium in which object is present. Here, this is the object. Now, this is the observer. So, refractive index of this is 1, air is 1 upon mu r. Mu r is the refractive index of that medium in which refracted rays are present. Like, guys, don't get confused over here. If I say this is the object, from the object, we say incident rays will leave. Okay. So, here, mu I will be this refractive index of this medium. And then it goes into the another medium. These are what we call the refracted rays. Okay. So this medium will be having the refractive index mu r. That's what I'm saying. If object is over here, so incident rays will be here. If object is here, incident rays will be here. Same is the case here. If this is object, incident rays will leave from object. If this is object, incident rays will leave from this object. So it will be 1 upon, we say 4 by 3. So it will be 36 into 4 by 3, 3 ones are 3 12s are. Now this will be 48 centimeter. So we say the apparent height of the bird is 48 centimeter. The apparent height of the bird is 48 and actual height is 36 centimeter. Now comes the concept of we say critical angle. Now comes the concept of we say critical angle. Okay. Everybody of you listen to me very carefully. Now guys, listen to me very carefully. What does critical angle actually say? See, I say you have got over here denser medium from the lower side and rarer medium from the upper side. If I say an incident ray comes from this medium and it goes into the rarer medium and it goes into the rarer. This is denser medium. This is we say rarer medium. Whenever the light goes from denser to rarer, we say it will bend away from the normal. It will bend away from the normal. It will bend away from the normal. Okay. So if light ray goes from rarer to denser, it will bend towards the normal. Okay. Now, if I say I will keep on increasing, guys, listen to me very carefully. If I say I will keep on increasing this angle of incidence, okay. Now we say angle of refraction. This refraction will also increase. So at certain value of angle of incidence, we say refracted ray becomes something like this, means it will make 90 degrees with the normal. This angle is what we call critical angle. This angle is what we call critical angle. So critical angle is that angle at which refracted ray makes 90 degrees with the normal. Okay. Angle R is 90. Now guys, if we use the Snell's law over here, everybody of you must be knowing what is Snell's law. Okay. So we say, listen to me very carefully. Snell's law says that mu I sine of I is equal to mu R sine of R. Mu I sine of I is equal to mu R sine of R. What does that mean? So Snell's law says that if light goes from one medium to another medium, let's suppose this is medium 1 and this is medium 2. Light goes from one medium to another medium. We say refractive index of this medium. Okay, let's suppose this is the incident ray over here. That is mu I. Then we say sine of angle of incidence will be equal to refractive index of this medium. Okay, mu R. Then we say sine of R, this angle over here. Okay, so same I am writing over here mu D. Okay, if this is denser medium, this is rarer medium. If light goes from denser to rarer, so mu D is the refractive index of denser medium into sine of theta C, because critical angle is over here, that is theta C. Mu D sine of theta C, okay, is equal to mu R sine of 90, because right now, see over here, this is the we say this is a refractive index of this medium, and this is critical angle, and this is this is refractive index of this medium, and this is critical angle, and this is angle of refraction, that is 90. So if we use it, so we can write it mu R sine of 90, sine of theta C will be mu R divided by mu D. This is the formula for critical angle, which you need to remember directly. Mu R is equal to sine of theta C divided by sine of theta C is equal to mu R divided by mu D. You guys need to keep this thing in your mind. Okay. Now there is a question on this one. If the critical angle for total internal reflection for a medium of vacuum, okay, critical angle in this case, ignore total internal reflection. If the critical angle in this case is 30 degrees, guys, listen to me very carefully. Let's suppose it says that there is a light which basically critical angle in this case is given as, we say, sir, 30 degrees. Okay. The velocity of light in the medium will be, listen to me very carefully. Critical angle over here is given as 30 degrees. Now see, what is the formula for critical angle? Sine theta C is equal to mu R by mu D. So can I say this is sine of theta C is equal to mu R divided by mu D over here, 110%. Okay. Forget about this also. Forget about this also. I'll be directly showing you the method. I'll be directly showing you the method. Let's suppose we say, sir, the light is, this is the normal. This is the normal. The light is basically moving from this medium, that is medium over here, which has refractive index mu. And it is basically moving from, we say this medium to vacuum. This is vacuum. And for vacuum, refractive index is 1. So we say it goes something like this. So this angle is, we say, sir, theta c. Now in this particular case, I want you guys to find the value of this refractive index. I'll tell you why are we finding the value of refractive index. Use Snell's law. What does that say? Mu I sine of I is equal to mu r, we say sine of r. Mu I is the refractive index of that medium in which incident rays are present. So that is mu. This has got refractive index mu. And then we say sine of theta c, because here you have got critical angle, is equal to mu r. Mu r is the refractive index of that medium in which refracted rays are present. So that is this, it has got refractive index 1. Sine of, we say r. Now guys, how much is the sine of r? R in this case is 90 degrees. Because at critical angle, how much is the value? That is 90. So we say this is sine of 90. Tell me one thing. Critical angle in this case is given as 30 degrees. So we say mu into sine of 30 is equal to sine 90 is 1. Sine 30 is 1 by 2. So we say mu will come out to be 2 if you take it over there. So means the refractive index of this is given as, we got it as 2. What we are supposed to find in this case, we say, what is the velocity of the light in this medium? What is the velocity of light in this medium? See, if you have to find the velocity of light in any medium, we know, sir, that will be velocity of light, speed of light in air or vacuum divided by a refractive index of that medium. That's the reason we were supposed to calculate the refractive index over here. So we say, how much is this? This is 3 into 10 raised power 8 meter per second divided by, what is refractive index? That is 2. So we will come out to be 1.5 into 10 raised power 8 meter per second. So this is the speed of light in that medium. I hope you got it. Guys, if you have not liked this session yet, I want you guys to like it as soon as possible, because liking the session is mandatory. One more important concept we say, that is what we call the prism. This is the concept of prism. Guys, see, you might have studied a bit about the prism, okay? Like you have got the prism over here. This is the prism that we have got. We say there is a light ray which basically enters this prism. This is the incident ray which enters this prism, okay? And we say if this light ray enters this prism, so this is air over here. This is the denser medium, because here you have got the prism. So whenever light enters from rarer medium to denser medium, it is bent away from the normal. On this surface, if you place normal, this will be the normal. So it is bent away from the normal. So it goes something like this. And then again, it moves from denser to rarer. So when the light moves from denser to rarer, it is bent away from the normal. So this will be normal. It is bent away from the normal. It is bent away from the normal. Okay. Okay. Yes. Now, guys, in this particular case, we say this is what we call angle of incidence. This is what we call angle of incidence. This is what we call angle of refraction in case of surface 1. And this is what we call angle of incidence on surface 2. This is what we call angle of refraction on surface 2, or you say this is also angle of emergence. And if I say this light ray would have gone straight something like this if this no prism was present over here. So final ray is this. So this is what we call deviation. Deviation in the original ray. Now if somebody asks you how to find deviation, simply remember in case of prism, this is the deviation. How much incident ray got deviated from its original path. That is I plus E minus A. Angle of incidence, angle of emergence, A is the angle of prism. Okay, and this A is equal to R1 plus R2. Remember this, R1 is this angle, R2 is this angle. And you can apply the Snell's law on first surface. You can apply the Snell's law on second surface. Because whenever the light moves from one medium to another, you can apply the Snell's law. Okay, now, let's talk about this particular question and let's find the answer over here. Find R1, R2, E and deviation. We have got the light ray over here. Light ray is falling at an angle of incidence. In this particular case, I is given as, we say, 45 degrees. Okay. If the light ray enters from rarer to denser medium, we say it is bent, I would say, away from the normal. Okay. And when it is moving from denser to rarer, we say it is bent, sorry, it is bent towards the normal. Here it is bent away from the normal. Normal will be this. This is what we call R1 and this is what we call R2 and this is what we call angle of emergence. And this will be the deviation. This will be the deviation. Now here we say angle of incidence is given as 45 degrees. Angle of prism is given as 75 degrees over here. Okay. And what we are supposed to calculate in this particular case is, everybody out there, what we are supposed to calculate in this particular case is, that is R1. How do we find the R1? We say apply Snell's law on surface 1. This is surface 1. That is mu I sine of I is equal to mu R, we say sine of R. Now what is mu I? Mu I is the refractive index of this medium. That is, we say 1 because this is air. Sine of I, that is sine of 45 degrees, is equal to mu R, refractive index of this prism, that is given as √2. Sine of R, we say sine of R1 because over here angle is R1. So this is 1 by √2, 1 by √2 into, this is 1 by √2 into this 1 by √2. So this is √2 sine of R1. So 1 by √2, that is 1 by 2. So R1 in this case will come out to be 30 degrees. Because when is the value of sine theta as 1 by 2? When theta is equal to 30 degrees. Okay. R1 came out to be 30 degrees. Now, if you got the value of R1, we know, sir, angle of prism is equal to R1 plus R2. Now, this is 75. This is, we say, 30 plus R2 in this case, we are supposed to calculate. So 75 minus 30 is how much? We say 45 will be, we say, value of R2. So this angle is 45. Okay. Now, if we have to find the angle of emergence, okay, how to find the angle of emergence? Everybody out there, listen to me very carefully. We say we'll use the Snell's law on second surface. Okay. I say on second surface. Can I say one thing? Listen to me very carefully. If I use the Snell's law on second surface, can I say one thing? That is mu I into sine of I is equal to mu R into sine of R. Now here, what is this is incident ray. So mu I in this case will be √2. So this will be √2 sine of I. I means this angle in this case, that is R2. R2 is 45 degree. So we say this is sine of 45 is equal mu R. Mu R in this case is this the refractive index of air. So we say that is refractive index of air is, we say, sir, 1, and we say sine of R. R means this angle of emergence. Here this will be R1 and this will be I angle of incidence. This will be angle of R. So that is sine of E over here. Okay. So we say this is a √2 into sine 45 is 1 by √2 is equal to sine of E. This and this will cancel. Sine E is 1. So E is, we say, 90 degrees. So angle of emergence in this case came out to be 90 degrees. Now, if somebody asks you to find the deviation, what is the formula for deviation? That is I plus E minus A. So we say deviation is I plus E minus A. Okay. Now you know this is 75 plus, what is the value of this is 90 minus A. I is not, I is 45. I is 45 plus E minus A. A is, we say, 75. Solve it and you will get the answer. Now, listen to me very carefully, my dear friends. Now comes the next topic, that is Q value of the reaction. Q value of the reaction. What does Q value of the reaction actually say? What does Q value of the reaction actually say? Just a second, guys. Okay. What does Q value of the reaction actually say? This is how much energy is absorbed or released. See, if I say I have got the two nuclei over here, this is A and B, and these two nuclei are converted into C and D. You have got two nuclei over here. We say A and B, they are converted into C and D nuclei. And this is what we call the reaction. And then we write over here plus Q. This Q will be either energy absorbed in the reaction or energy released in the reaction. Okay. So when this is a reactant nuclei, these are what we call product nuclei. When reactant nuclei is converted into product nuclei, we say in this reaction, some energy may be either absorbed or some energy may be either released. Okay. Okay. Now, how to find this Q value of the reaction? We say simply it is mass of the reactants minus we say mass of the products multiplied by we say C square. Multiplied by we say C square. Whatever is the mass of reactants minus mass of products and multiplied by C square. Okay. Now, if we said, sir, this Q is mass of A plus mass of B minus mass of C plus mass of D into C square. One more thing I just want to tell you over here. If mass of A plus mass of B came out to be greater than mass of C plus mass of D, in that case, we say Q value is positive. Clearly, you can see over here. If I say this is greater than this, let's suppose this is 10, this is 5. 10 minus 5 is plus 5. So in this case, Q value will come out to be positive. And if Q value is positive, remember guys, energy is released. So it's an exothermic process. And if mass of A plus mass of B is coming out to be less than mass of C plus mass of D, in that case, we say Q value is negative and we say energy is absorbed in that case. So we see this is an endothermic process. And this was the Q value of the reaction in terms of mass. If somebody asks you to write the Q value of the reaction in terms of binding energy, so we say it is simply in terms of binding energy. If we have to write it, we say this Q will be, so this Q will be, that is binding energy of products minus we say binding energy of reactant. So binding energy of products minus binding energy of reactants will give you the Q value of the reaction in this particular case. Okay. Okay. Now guys, let's see a question on this particular topic. There is a reaction that is given. This is 3Li7 plus 1H1. It gives us, we say 2He4 plus 2He4 plus Q. So we say this is the reaction that is given over here. Okay. And in this reaction, we are supposed to find the Q value of the reaction. See, what is the formula? That is binding energy of products minus we say binding energy of reactants. So binding energy of products minus binding energy of reactants will give you the Q value of the reaction. Okay. Now the question here is, what is mentioned in the question? It is saying that binding energy per nucleon of 3Li7 is 5.60 and for 2He4 is 7.06. What does that mean? That means binding energy of every nucleon of this atom, of this nucleus. Okay, if we say 3Li7, so we say here binding energy per nucleon is given as how much? We say 5.60. So means for every nucleon of this nucleus, binding energy is 5.60. How many nucleons are in this nucleus? We say, sir, 7, because mass number is 7. So 7 will have got how much binding energy? You say, sir, that will be binding. This is the reactant, okay? That will be 7 into 5.60. Okay. Binding energy of products. So now, If we talk about 2He4, it says that binding energy per nucleon of 2He4 is how much? We say that is 7.06. Now, how many nucleons are there in products? 4 plus 4 is 8. So in 8 nucleons, how many binding energy, how much will be the binding energy? That is 8 into, we say 7.06. Okay, you solve it, it will be 17.4 MeV. This is how do we actually calculate. So this was basically given the binding energy of every nucleon. For Li7, 3Li7, we say for every nucleon binding energy is 5.60. So for 7, it will be 7 into 5.60. Similarly here also. Let's talk about the concept that is forward bias and reverse bias. Guys, see, if let's suppose we have got a PN junction diode over here. If let's suppose we have got a PN junction diode over here, means P-type and N-type semiconductor. Okay. Now we know, sir, in this case, there is a depletion region. Okay. Now, guys, listen to me very carefully. Majority charge carriers in case of N-type semiconductors are what? We say electrons. You must be knowing that. In case of N-type semiconductor, we say majority charge carriers are electrons. And in case of P-type semiconductor, we say majority charge carriers are holes. Okay. Now, if you connect a battery over here, such that this P side, this higher potential is connected to P side, and negative terminal is connected to N side. Okay, this is what we call forward bias. This is what we call forward bias. And I will tell you how does current flow in the forward bias. We say this negative charge will basically do one thing. It will basically kind of send negative charge over here. This positive terminal will kind of send positive charge over here. This negative will repel this negative. This positive will repel the holes, because we say holes also have got the positive charge. So when they are repelled, we say here depletion region decreases. If depletion region decreases, these electrons will get recombined. These electrons will move to this side. Okay. Now, if these electrons move to this side, they will flow through the battery and will come over here once again. Once again, they come over here. Once again, they will flow. And this is how does the current flow in the forward bias. What I want you guys to remember in this case is forward bias means when P-type semiconductor is connected to positive terminal. Like I say over here, this is the symbol of PN junction diode. Here, P-type semiconductor, if this is connected to positive terminal, means it is forward bias. And this is N side, forward, this is N side. If N side is connected to negative terminal, means this is the reverse bias. Okay. And when it comes to the reverse bias, guys, see. If I say P side is connected to lower potential, negative charge, and N side is connected to, we say, higher potential, that is positive terminal. This is what we call the reverse bias. This is what I want you guys to remember here. Now, let's talk about the questions which were asked over here. Guys, see, which one of the following represents the forward bias? See, this is, I'll write over here. This is P side and this is N side. P side is connected to, we say, 3 volts. 3 volts is lower potential, 5 volts is higher potential. 5 is greater than 3. Here, P side is connected to lower potential, N side is connected to higher potential. We say this is reverse bias. Let's see over here. This is P side and this is N side. Here, P side is connected to 0. N side is connected to -1. So we say this is forward bias in this case. Okay. Now this is P and this is N. In this case, P is connected to -4, N is connected to -3. This is also, we say, reverse bias. In this case, we say this is P side and this is N side. P side is connected to -2, N side is connected to, we say, +2. We say this is also a reverse bias. Why? Because this is, we say, in this case, lower potential, this is higher potential. So option B is the correct option in this particular case. I hope you got it. I hope you got it. The increase in the depletion region in the PN junction diode is due to, I will tell you the answer of this. Guys, see. Everybody of you must be knowing that when it comes to the PN junction diode, listen to me very carefully. We say holes have got P-type semiconductor contains, we say, majority charge carriers are holes. N-type semiconductor contains electrons. We say this positive charge will send over here. This is negative charge. This is not positive. This is negative. It will send negative charge over here. Positive terminal will kind of send positive charge over here. Now tell me one thing. This positive will attract this N side. This negative will attract this N side. So this, we say in this case, depletion region will increase. Depletion region will increase. In case of forward bias, we say depletion region decreases. Here, depletion region will increase. So answer in this case is, this was a question in NEET 2020. So, and the increase in the depletion region in PN junction diode is in the reverse bias. Let's talk about this NOR gate. Let's talk about this NOR gate. Let's talk about this NOR gate. Guys, what is this NOR gate? Everybody of you listen to me very carefully. Everybody of you listen to me very carefully. Now see, if I say, I have got over here, this is an OR gate, okay? The work of OR gate is to basically add. Means, if you give input A over here, you give input B over here, its job is to add these two inputs. So it will do A plus B, it will add them. Okay, this is OR gate. And then if you connect a NOT gate over here, the work of NOT gate is to do the inverse. So if A plus B is entering this, if A plus B is entering this, we say output in this case will be A plus B bar. Whatever you send the input, it will do the inverse of that. If I say I am sending, let's suppose A over here, what will be the output of this NOT gate? That will be A bar. Okay, so we say NOR gate, it is combination of OR plus, we say, sir, NOT gate. What is the work of OR? It will add the two inputs. What is the work of NOT? It will basically do the inverse. It will basically do the inverse. Okay. Okay. Now, guys, listen to me very carefully. Listen to me very carefully. When it comes to the circuit symbol, what is the circuit symbol? We say we make the circuit symbol in this particular case something like this. Okay, this is the circuit symbol over here. So input over here is A, out input over here is B. Okay, and we say Y is equal to A plus B whole bar. Y is equal to A plus B whole bar. This is the final output. This whole is considered as NOR gate, and this is the symbol. So make this OR over here. Instead of this, we make a ball only. So this is the symbol of, we say, NOR gate. Now guys, listen to me very carefully. Let's talk about truth table. What is the truth table? Means if you give the input 0, 0, okay? If you give the input 0, 0, first this will be 0 plus 0 is, this will be 0. So we say OR gate will add them, 0 plus 0 is 0. Then we say NOR gate final output. What is the final output? Final output is Y is equal to A plus B bar. So that will be 0, 0 bar is, we say, 1. That is 1. It's 0, 1. 0 plus 1 is 1. So we say 1 bar will be 0. So basically, this is the truth table of what? NOR gate. This is the truth table of NOR gate. Let's talk about the NAND gate. When it comes to the NAND gate, it is combination of AND plus NOT. When you basically join AND gate with NOT gate, it forms which gate? We say NAND gate. And this is the symbol of AND. If you give input A, input B, it will multiply them, A dot B. And then you put NOT. What is the work of NOT? It will just put the bar. So its symbol is directly this one. This is the symbol of NOT gate. Okay, this is the symbol. Final output in this case is A, B bar. Can you make the truth table? See, if A is 0, B is 0. See, what is the output? Guys, see, output of NOR is, output of NAND is A, B whole bar. If A is 0, B is 0, what is output? That is A into B. That is 0 into 0 is 0. So 0 bar is 1. So final it will be 1. 0 into 0 is 0. 0 bar is 1. 1 and this is 0. This is the truth table. Now let me show you this question. This is the question which was asked in NEET 2019, and it is extremely important. The question is extremely important. The correct Boolean operation represented by the circuit diagram is, okay, it says that we are given a circuit over here, this circuit. It says that this circuit represents which gate? What this circuit represents which gate? Let me show you. Let me show you. How do we solve this question? I will show you. Let's do one thing. Let's make the truth table. Let's make the truth table. Okay. So we say, I'll tell you how do we make the truth table. This is K1 over here. This is K2 over here. This is K1. This is K2. Okay. And then we have got the bulb over here. Then we have got the bulb over here. Everybody of you listen to me very carefully. Everybody of you listen to me very carefully. Okay. 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 Guys, see. We say current always flow from higher potential to lower potential. Lower potential is 0 volt over here. Now, and current always prefers that path in which there is less resistance. Current always prefers that path in which there is less resistance. Now see, we say current will flow something like this. If I say in this particular case, I will keep this key on and this key on. Listen to me very carefully. This is on, this is on. So current can now flow through this path, something like this. Why would the current flow through the bulb? As bulb has got resistance, so current will prefer this path where there is no resistance. So in this case, no current flows through the bulb, bulb will remain off. 1 means on, 1 means on, 0 means off. Okay. Now guys, listen to me very carefully. If I say in this particular case, I'll keep this on, this off. So we say this is on, this is off. Current will flow, but it cannot flow over here. Why? Because this is off. So current has to flow through the bulb, so bulb will be on. Similarly, if this is off and this is on, so bulb in that case will be on because current cannot flow through this path. If both are off, this is off, so then current has to flow through this path, so bulb will remain on. And if you compare this truth table, don't you think it is exactly similar? It is exactly similar to NOR gate. When you have got a 0 and 0, you have got final answer 1. When you have got 1 and 1, you have got final answer as 0. Now see, when you have got 0 and 0, you have got answer 1. 1 and 1, you have got 0. And this is, we say, sir, NOR gate. Means this circuit exactly behaves like a NOR gate. Okay. Next question, this one. Here, you have got, I'll make it once again over here. Okay, this is given as plus 6 volts and this is 0 volts. Current flows from higher potential to lower potential, and this is bulb. This is, we say, K1 over here. This is K2 over here. In this particular case, you guys are supposed to tell me which gate is this. Let's make the truth table. Let's make the truth table. We say this is K1, this is K2, and this is bulb. K1, K2, and this is bulb. K1, K2, and this is bulb. Okay. Now see. If I say I'll keep the K1 on, let's suppose I'll keep the K1 on. Let's suppose I'll keep the K2 also on. See, if K1 is on and K2 is on, what will happen to the bulb? Current prefers that path in which there is less resistance. So current will flow. Let me take this color. Current will flow. It can flow through this path. It can flow through this path. But it will not flow through the bulb. Why? Because bulb has got resistance. So bulb remains off. Okay. Now if I say, let's keep this on and this off and this on. Let me show you for these two. Now guys, see, if current flows something like this, we say if K1 is on, means this is on. Current can flow through this path and will reach over here. So in this case, bulb remains off. We say bulb is off. That is 0. Now, if K2 is on, so current can flow through this. In this case also, bulb is off. Now, listen to me very carefully. If I say this is off and this is off, this is off and this is off, in that case, current has to flow through this path, that is through the bulb. Bulb will remain on. And if you check, this is the truth table of, we say, sir, this is NAND gate. Compare the truth table of NAND gate, that will be exactly similar to this. That will be exactly similar to this. Okay, 0, 0, 1. Let me show you 0, 0, 1. When you have got 1, 1, 0, 1, 1, 0, and 0, 0, 1. 1, 1, 0, 0, 0, 1. Last question from the logic gates. This was the question which was actually asked in NEET 2018. NEET 2018. See, we say we have got A input over here, B input over here. This is, we say, AND gate. This is, we say, AND gate. This is also, we say, sir, AND gate. And this is, we say, sir, OR gate. Its job is to multiply. Its job is to multiply. Its job is to add. Now see, if A input is going over here, it will directly go in A input. Now this B input is over here. We have got NOT gate. What is the work of NOT gate? Its work is to do the inverse. So here it will be B bar. Now if A is coming, this is A over here. This will basically do the inverse of A. This will do the inverse of A. Now B is coming, so this will be B. Now tell me what will be the output in these two cases. What will be the output in these two cases? See, guys, A and B, this will multiply A and B bar. So it will be A, B bar. Now this also, this will multiply A bar and this B. Now this A bar and B will go into the OR. What is the work of OR? Its work is to add. So final output Y will be, that is A, B bar plus A bar B. So this is the final output that you guys need to keep in your mind. And this is over here. Okay. 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 This concept, that is LCR circuit, very much important from, we say, AC chapter. From alternating current chapter, we say this concept is very important. That is series LCR. Series LCR means if you have got a circuit over here in which you have got an inductor connected, you have got an capacitor connected, you have got a resistor connected. This is, we say, L, this is C, and this is R. Inductance, capacitance, resistance. Okay, that's why we say this is series LCR circuit. Okay, now see, guys, if you have not liked this session yet, I want you guys to like this session. Okay, let me check the likes. How many likes are over there? Everyone means everyone. Oh, guys, make it. I want you guys to make it 1.5K right now. I want you guys to make it 1.5K right now. Everyone means everyone. Everyone means everyone. Make it 1.5K right now. Okay. Smash the like button. Smash the like button, everybody. Now see. We say, let's suppose you have connected an AC source to this. Okay. AC source means V is equal to V naught sine omega t. This is the voltage of AC source. And voltage across this, current across, voltage, potential difference across this is VL, VC, and VR. Now listen to me very carefully. Here I want to revise certain things over here. Listen to me very carefully. We say, guys, you might have studied one single thing. What is that? You might have studied one single thing. If let's suppose you have got this, that is, guys, see, if you are representing this voltage VR with the help of phasor diagram, okay? So we say we represented something like this. This is VR. We know that, sir, this VR and I, they are always in same phase in case of resistance. Guys, remember, Here, there will be a little bit of confusion to those students who haven't studied this before. Okay. So we say voltage across the resistance is always in the phase of current. If current is in this phase, we say voltage will be in the same phase. Now see, when it comes to the voltage in case of inductor, we say that leads current by pi by 2. Means if I say leading pi by 2 means if this is the current, we say voltage will be something like this. It is leading by pi by 2. So in case of inductor, we say potential difference leads by pi by 2. Okay. And in case of capacitor, we say potential difference lags by pi by 2. So it will lag by pi by 2. Okay. So this is what we call the phasor diagram of LCR circuit. Phasor diagram of LCR circuit. Okay. Now guys, listen to me very carefully what I'm trying to say in this particular case. If I say this VL is greater than this VC, so then resultant will be VL minus VC. This will be VR, and net in this case will be V net is equal to VL minus VC whole square plus VR square. This will be net voltage in that case. Net voltage in that case. Next. Now, if we make the impedance diagram, listen to me very carefully, guys. If we make the impedance diagram, how do we make the impedance diagram? See, when it comes to the voltage in case of resistance, we say V is equal to I into R. So in case of capacitance, we say V is equal to I into XC. In case of inductance, we say I into XL. This XC is what we call capacitive reactance. And this is the resistance in case of capacitor. This is inductive reactance. This is the resistance in case of inductor. Now you can cancel this I and I. So finally you can write this will be something like this. I'll show you. This will be, we say XL. This will be, we say R, and this will be, we say XC. And this will be, we say, sir, current I. So what I am trying to say in this particular case is directly remember, if you have to make the voltage with the help of this arrow, okay, or you have to make the resistance, we say resistance, here current is in this phase, we say resistance will be something like this. This will be XL, and this is what we call the phasor diagram of LCR circuit. Okay. Now, if I say, guys, see, if I say XL is greater than XC, XL is greater than XC. So can I say in that case, this will be the resultant diagram. This is XL minus XC. This will be R, and this will be resultant. So in this particular case, this will be V net is equal to under root. Sorry, we say Z is equal to, Z will be net resistance. That is XL minus XC whole square plus we say R square. This is what we call the impedance. Impedance means the resistance in case of LCR circuit. So that's what I'm trying to say over here. Okay. See, if this is XL minus XC, this is R, this will be Z in this particular case, and this will be sir phi. So Z is the net resistance of, we say, LCR circuit. For LCR circuit, net resistance is Z, and this Z is simply XL minus XC whole square plus we say R square. Okay. And if somebody asks you find the value of this phi also, tan phi, that is XL minus XC, that is this perpendicular, that is XL minus XC divided by this base is R, so divided by R. Okay. Okay. And there is one more thing, that is resonance condition. There is resonance condition. See, what does resonance condition actually mean? Directly, guys, resonance condition in case of LCR is important. Please, just for 2 minutes. This is LCR circuit. This is the impedance diagram of LCR circuit. Okay. One thing I just want to tell you. If we have got an LCR circuit over here, if I say this is the impedance diagram of LCR circuit, this is XC, this is we say sir R, and this is we say sir XL. If I say, guys, if remember this is the impedance diagram. This is important. Whatever I said till now about the LCR circuit, forget that. Remember this. If I say XL is greater than XC, then we say this will be the resultant diagram. This is XL minus XC. This will be R, and this will be the net resistance. That is what we call impedance. So this will be under root of XL minus XC whole square plus R square. Now remember, this is here we say LCR. In this particular case, LCR is inductive in nature. Okay, and if I say if XC is greater than XL, means this is greater than this, can I say in that case net phasor diagram, net impedance diagram will be XC minus XL? This will be R and this will be the net resistance Z. So we can say here it will be Z is equal to under root of, we say, XC minus XL ka whole square plus R square. So can I say in this particular case LCR is capacitive in nature? We say here LCR is capacitive in nature. That's what I wanted to explain over here. And if by chance I say this XL, this is, we say, sir, R, and this is, we say, sir, XC. If by chance I say XL becomes equal to XC, can I say this will get cancelled with this one? What will be net resistance in that case? That will be Z. That will be Z. Z is equal to R. So this is what we call a resonance condition. A resonance condition. This is what we call resonance condition. This is what we call resonance condition. This is what we call resonance condition. And can I say at resonance condition XL is equal to XC? Inductive reactance is equal to capacitive reactance in case of LCR circuit? Yes. So guys, remember always this XL is equal to omega into L. And this XC is equal to 1 upon omega C. So here it will be omega square. See, it will be omega. So we say this will be omega into L is equal to 1 upon omega C. So this will be omega square is equal to 1 by LC. So we say omega is equal to 1 upon under root of LC. Okay, LC. And this is what we call resonant angular frequency. And you can also say this omega is 2 pi f, that will be 1 upon under root of LC. So f will be 1 upon 2 pi. So f will be 1 upon 2 pi under root of, we say, LC. This is what we call linear resonant frequency. This is what we call linear resonant frequency. Okay, I hope you got it. I hope you got it. Like it is explained over here. Okay. One more concept is over here. And this is the last concept and we are done. Listen to me very carefully. Guys, see, if I say I have got a hollow sphere over here. This is a hollow sphere. Okay. Hollow sphere means in which charge is present on its surface. And radius of this sphere is capital R. And I am asking you to tell me the electric field outside the sphere at small r distance. Always remember, electric field because of the hollow sphere outside will be simply E is equal to KQ divided by small r square. Same as the formula which we use in the point charge. Why? Because at very far a distance, we consider this sphere as a point charge. Okay. Now, if I say at surface, can I say small r is equal to capital R? 110%. Yes, sir. So we say electric field will be KQ divided by capital R square. And if I talk about inside, guys, inside charge is, we say, sir, 0. Inside charge is 0. So electric field inside will be 0 because there is no charge present. If there is charge, there is electric field. If there is no charge, there is no electric field. That's the reason I'm saying electric field inside is 0. Okay. And if somebody asks you to plot the graph will be simply something like this. This is outside. Why? Because outside E is inversely proportional to, we say, sir, R square. Inside E is, inside we say at this, inside E is 0. Next. Let's take a look at the question which is mentioned over here. That's the reason I explained that concept. Here, the question says that we have got two hollow spheres, this bigger one, this smaller one, and there is a charge placed over here that is plus Q at the center, point charge. The radius of this sphere is given as capital R, okay? And the we have got the radius of bigger sphere is given as 3R. I am asking you to tell me the electric field at point P and electric field at point S. Listen to me very, very, very carefully. Let me show you how do we exactly solve this particular question. See, I will tell you. If I say at point P, electric field at point P, we say when it comes to the point P, this point P lies inside the bigger sphere. So means the charge on the bigger sphere will be on its surface. Because of this bigger sphere, electric field at point P will be 0. But because of this sphere and this charge, electric field at point P will be there. That is K Q. What is the value of Q over here? Q plus 2Q, that is 3Q. Divided by R square. What is the value of R at what distance you are finding? That is 2R whole square. 2R whole square. So this will be 3KQ divided by 4R square. So what I am trying to say is that electric field at point P will be 3KQ by 4R square. So because of the bigger sphere, there will be no electric field over here. For inner sphere, this point lies outside the sphere. So we can use outside formula. How much is outside formula? That is KQ by small r square. Instead of Q, you have got 3Q over here. Instead of R, you have got 2R, 2 capital R square over here, whole square. Okay. Now, next. If I ask you to tell me what is the electric field at point, we say S. Electric field at point S. Guys, remember one thing. When it comes to the point S, so we say if you draw a sphere over here, inside that sphere, we say CC. For this bigger sphere, this point is outside point. For this smaller sphere, this point is outside point. So electric field will be K. Instead of Q, Q is how much? Charge on this sphere, that is 3Q plus 2Q plus Q, that is 6Q. Divided by, we say how much distance is it? 4 square, 4R whole square. So I can say this will be 6KQ divided by 16R square. And even if somebody tells you, my dear friends, find the electric field inside at R by 2 distance. Now see, at R by 2, let's suppose this is X, electric field at X. Guys, see, if I see at this X point, listen to me very carefully. This X point lies inside this hollow sphere. It lies inside this hollow sphere. So electric field because of this hollow sphere at point X will be 0. Electric field because of this bigger sphere at point X will be 0. So because of this point charge, electric field will be at, we say, R by 2 distance. So that will be KQ divided by R by 2 whole square. And that will be 4KQ divided by R square, because R by 2 whole square is R square by 4. Okay, this is a very important question that you guys need to keep in your mind. And along with this, let me tell you something. If we have got a solid sphere, okay, this is filled with the charge, okay, positive charge over here, that is Q. If I say the radius is R, how much is electric field outside? Remember, electric field outside will be KQ divided by small r square. Same as hollow sphere, because for outside point, we consider both as point charges. If I say on the surface, we say small r is equal to capital R. If you keep on reducing this R, on surface small r becomes capital R. So can I say that electric field will be KQ divided by capital R square? Yes, sir. And my dear friends, if I say inside point, right now inside point, at inside point electric field is not 0. Why? Because charge is present inside. So electric field inside will be K cube by R cube into small r. And if somebody asks you to plot the graph between E versus R in case of a solid sphere, what will you say? This will be the graph. So we say E is directly proportional to small r inside. You can clearly see. And E is inversely proportional to small r square. We say outside. I hope this is crystal and clear. Everybody of you, do not leave before liking this session, okay? Thank you so much, everybody of you. Thank you. Okay, I want all of you to basically comment down below once I end the live stream, okay? Once I end the live stream, I want all of you to comment down below, which is very much important, okay? Till then, take care and bye-bye, okay? So do comment afterwards in the comments down below. How was the session, each and everything, okay? I hope this was beneficial for the students out there. So take care and bye-bye. I will be waiting for your comments, which you will be putting down. So take care and bye-bye. Take care and bye-bye.